first. Okay, great. So before we begin today, let me just go through the announcements for the class. Can you see my screen?
Yeah, we can. Yeah.
Okay. So quick announcement: will be no class on September 15th, this Thursday. So please use this time to complete your first team assignment, which is the essentially the literature review of the problem area that you've chosen for your team. And also note that the lecture schedule has changed slightly. I'll show you below. But most importantly, don't forget to meet with your technical mentors this week, because they will be giving me feedback about your work in the teams, and that will affect your grades. So make sure you don't forget to do that. And it's just 1 hour this week. So just quick note on the schedule. So we are here. We're going to talk about optical design for recycling today.
Dr. Menon, we cannot see your screen.
Let's see. Oh, how about now?
Yeah, it works now.
Okay. So let me just say, as making the announcements here, you can see on the website, there will be no class on Thursday. Use this time to work on your first team assignment. The schedule has changed slightly. I'll show you in a minute. But again, don't forget to meet with your technical mentors. They will be providing me feedback on your performance in the team. So it's just one hour this week. At the end of today's lecture, if you have any additional questions, we can go over the assignments and so on. So I will be around if you have any questions. Okay, so just a quick note on the schedule. Today we're going to talk about optical design for recycling. The lecture notes are here. The article we'll talk about is also here, so if you should take a look at it. Thursday there's no class. Next Tuesday we will have a class on the concepts of non-imaging optics, and the following Thursday we have your graded assignment 1. So please be aware of that short timeline. And the following Tuesday, we have a second lecture on non-imaging optics, and then following that, we have a lecture on light tools. So all of you should have received an email about how to obtain the license for light tools. Make sure you obtain it by September 29th. Okay? And if you have any questions, feel free to ask me or Naren as soon as possible. And then, of course, most importantly, the week after that is our midterm. So we'll have a review on October 4th and actual midterms on October 6th, which is right before fall break. Okay, the rest of the schedule really hasn't changed, but I just wanted to point this out. Keep this in mind with regard to your schedule. Okay, first, before I begin, are there any questions?
No, you can carry on.
Okay. So let's begin the lecture 7, which is it's an interesting topic because it's a topic which is very discussed very little actually in optical engineering classes. This idea of how optics is used for recycling. So before we jump into it, I'm following this article by Nord Bryn in Optics and Photonics News on June 2012, which is actually posted on our class website. So I highly recommend you take a look at it, and we'll talk in some detail about this in this class. At the end of the class, I will also present to you one final video from a team that worked on this topic for its project a couple of years ago, and which will also give you an idea of what I expect as a presentation at the very end of the class. And we will also have some extra time at the end to talk about your first assignment if you have any questions, since I was intending to do this next Tuesday, but because of the schedule changes, I won't have time. Okay, so what is the application we're talking about? There are, of course, many applications for in applying optics for recycling, The particular one we'll talk about first is what's called a reverse vending machine. Now, of course, everyone knows what a reverse vending machine is. It's basically something that takes in a recyclable material and provides some value to the customer, which could be in the terms of store credit. So that's what it looks like. This is an extremely large industry, and there are very, very large companies in this space, which you probably have never heard of. I hadn't heard of until I actually read this article. So the main companies are in Wipco, if you're interested, in the US, Wincor, Nixdorf in Germany, and Tomra in Norway. So the particular article that we're talking about is written by the founder of Tomra. And this is very interesting because it gives you an idea of a very specific challenge in resource recycling, and where optical engineering can make a very, very big impact. Now, resource recycling, of course, is very important from an energy point of view because it's a way to reuse materials. So what is the main challenge? So if you think about this, let's just think about recycling drink containers. Drink containers come in extremely different variety of colors, shapes, materials. It can be glass, it can be plastic, various types of plastic. It can be aluminum. There's a huge variety of these. All of these need to be identified and sorted appropriately at extremely high speeds and at high efficiency, that in a very, very low cost manner, in order for such an industry to actually succeed. And not only that, it turns out you also need to separate these materials into accurate categories. And this is important because if you understand what happens to these materials after they are recycled. So typically, there are two options for these materials. One is these materials could be essentially destroyed or converted into constituent materials, like glass could be broken down into little glass frit and then can be used for other applications. So, or aluminum cans can be essentially smashed into little pieces for transportation and then recast into something else. The other option, for example, which is less popular now, is the fact that glass bottles could be completely reused. They're just not destroyed; they're just cleaned and reused again. And that used to happen; it doesn't happen so much anymore. In any case, it turns out the return on investment is highly dependent upon how precisely you can actually sort these into various categories. In other words, the materials markets that actually pay money for aluminum or different kinds of plastics pay a higher premium for materials that are very well sorted. Okay, so that's the key idea. We need to be able to identify and sort the materials at extremely high speeds. And the solution is optics. I mean, there are many ways to do this, but optics is the most prevalent and most successful approach here. Now, if you think about this, actually, before I go into this, if you have metallic objects like aluminum or iron-based materials, you can, of course, use electromagnets. So you can separate things out. And that happens. Unfortunately, of course, electromagnets take a lot of energy because you need to pass current and you need a pretty strong magnetic field in order for scrap metals and things like that. So it's expensive and it's not as fast as optics. And of course, it cannot deal with plastics. So one of the first approaches is basically shape measurement. And shape measurement essentially means, okay, could we just look at what's inserted into a machine and understand whether it's a cylindrical can or it's a very special shaped bottle or something else, egg cart, whatever. Now, of course, for good sorting to happen at high speeds, very high accuracy is needed. This can be done in various methods. One can think of today, for example, if you have played video games on a Microsoft Kinect, the technology used in the Microsoft Kinect can actually be used for shape measurement. So today, what we are talking about is consumer electronics products can actually do shape measurement. And this is possible because there is an optical device in there which does a computational shape measurement. We won't really talk about it because it's a little bit complicated, a little bit outside the scope of this particular class, but keep that also in mind. So all of you probably, and some phones actually now have this capability as well for depth and shape measurement. But the simplest thing you can think about is basically a photocell on a conveyor belt. So you can see a conveyor belt here, and there's a bunch of lasers with a photocell. So there's one on each side. As the material or the bottle or can, whatever, passes by, the laser is interrupted, right? And by knowing the relative position of the photocell, the interrupted signal can be decomposed, and some algorithms can be applied in order to essentially see, okay, the bottle is this long, the can is this long, or whatnot. And by knowing, performing a variety of calibration experiments, it's able to, these types of machines are able to sort different types of machines. So it's a very, very simple optical device in a sense. So it's essentially measuring a point in space and in time. And we know the speed at which the conveyor belt is moving. So by knowing the speed and the signal that happens at each point in time and space, you're able to actually get the shape of the material. So another more sophisticated approach is what's called laser range finding. This is a bit more complicated, but it's much more precise and can be done at a much longer distance. It doesn't need to be on a simple conveyor belt. So an important application for a technology like this, for example, is to scan large crates. So in large recycling facilities, you have essentially crates containing large numbers of bottles or cans and so on. And an example is shown here. And in that case, if you simply put it on a conveyor belt and pass through, obviously you cannot see what's inside the crate, so you can't really measure it. So you need to have some way to do three-dimensional imaging. And that's what an example is shown here. This is essentially a scanning laser rangefinder. So essentially you have a laser that moves in an arc, as shown here, and essentially probes at different angles onto this crate. And at each angle, the laser is able to find the topography. So it builds up a three-dimensional image of this crate, and from that, and using some algorithms, you're able to essentially count, okay, I have 56 different kinds of bottles in there, and so on. For scale, for example, this is 50 centimeters in diameter from here to here. Now, how does rangefinder work? So rangefinder works in a very, very relatively simple way to understand. So it's a laser, and the laser is modulators. What that means is that you basically send in a sinusoidal signal to the laser. So the laser goes up high intensity, low intensity, high intensity, low intensity, very, very high frequency. The light that is reflected back from a target is also modulated, but the phase of the modulation is slightly shifted depending upon how far away the target is. So if the target is close, you get a somewhat different modulation, whereas if you if you're a little bit further. This is very similar to, for example, a Doppler shift. A Doppler shift in acoustics, it's a very similar thing that happens in optics as well. And of course, then you have some algorithms which figure out the distance based on a measurement of this phase shift. So clearly, the measurement of the phase shift is a relatively complex equipment. You need to be able to measure a phase of light. Which means it's not just a simple photocell. You need to be able to have a reference beam and a signal beam. You need to interfere them and so on. And again, it's a little bit outside the scope of our class, so we don't need to really understand the technology, but keep just approximately understand how it works. By the way, some of you may be familiar that this is very commonly used in when you play golf. So I picked this video just to illustrate a commercial product that you can see. So let me just quickly change the audio from here to the
Welcome to the Ely Callaway Performance Center. My name is John Deegan, and I'm one of the club fitters here at the test center. And today we're talking about an important piece of technology for Callaway Golf, the Callaway LR550 rangefinder. And it's fairly simple to activate. Simply press the power button down. It puts the laser into continuous mode. And you can scan the pin or whatever else you're after. So this particular pin on our range is 88 yards away. So this takes a little bit of the guesswork out of the round of golf for the player. They don't need to walk around and look for a sprinkler head. Simply shoot your pin, get your number, and play on.
Okay, so you can see basically it has a laser. It has two holes. It has two apertures. It has a laser which is shot out of the device, and when the light comes back, it is detected by a detector at the bottom. And there's some algorithms which figure out the distance. So it's very similar. And by the way, the most exciting application in my opinion, of laser rangefinder is autonomous vehicles. So if you have ever seen a Google self-driving car or some of the other self-driving cars, you will see a big device on top of the roof of the car, and it rotates. It's basically a scanning laser rangefinder. It's like a radar, but with light waves. So it essentially builds up this three-dimensional map of what's around the vehicle. So very similar technology. Okay. So of course, the laser range finding approach is a very effective approach. Unfortunately, it's very expensive because you need to have a laser, you need to have a fairly complicated detection system because you need to look at shape. But it turns out, since then, there was an evolution of algorithms that you can actually do stereo vision systems, which basically means that you combine two cameras and image processing for fast, accurate shape recognition. A good example for this, for example, is the if any of you have seen the Intel RealSense camera. So Intel had recently announced, actually last year, a developer kit for a camera, which is a little handheld device like your phone, but it has two eyes on it. And the idea is that with the two eyes, you're able to essentially take a picture of a scene and build the three-dimensional shape of a room or whatever. And this basically takes into account perspective. So, if you only look with one eye, you cannot really tell. You don't have depth information, so you don't have three-dimensional shape information. Whereas if you look with two eyes, you actually, your brain, your two eyes see two images from two different perspectives, and your brain essentially overlays them, and you're able to perceive the three-dimensional world. This is, of course, very important in applications like virtual reality and augmented reality, where you actually have to present two images to the two eyes. To essentially fool your eye into believing that you're looking at an immersive medium. This is the exact same technology that can be applied also for shape recognition in sorting these materials. So the way that's done is very similar to this. Instead of having a single photocell or a single laser rangefinder, you basically have two cameras, and then everything else is done in image processing. So if you have two cameras which are looking at a can or a bottle, you can actually tell the difference between a big can, small can, large bottle, small bottle, etc. So it essentially the hardware costs become very low, and all the complexity goes into the software. So this is really the state of the art at this point in time. But we should also one of the purposes of our class is not just the technology, but also to understand from a commercialization point of view or from a market level point of view. So if you actually carefully read the article, there's a lot of good information about how the consumer requirements drive the technology. So, recycling markets are very unique because there's things that you don't usually think of. For example, this single-use device where, like an aluminum can, where you only use it once and then it's turned into something else, or you can have multi-use containers, which are basically reused again and again. Also, what's interesting is also there's this political element of the container deposit. So where there are about 10 or 12 states in the US where there's a container deposit law, which basically means that when you go buy a can of Coke or whatever, you pay an extra 5 cents or something like that, which goes into a deposit with the government. And this extra 5 cents is something you get back when you return that can for recycling. So, and of course, not all states or countries do this. It's much more common in Europe. About 10 states in the US do this. But what's really interesting with this model is that clearly when such a deposit-based model exists, then there is much more incentive for the customers to return these cans for recycling or reusing or whatever. So that drives this recycling market. Now, what's really interesting is that, of course, not 100% of the customers actually return the cans because some of them don't want to be bothered with it. So if you think about it, there's extra money, which basically is free money. So the people who do not participate in the deposit market actually end up financing the equipment, which is very expensive for very large scale recycling. So it's a very interesting business model and very counterintuitive to some extent. Now, if you think about the vast majority of the markets in states like Utah, where in our state there is no deposit, so then why do people recycle? The recycling still exists. Of course, Salt Lake municipality recycles. And the reason is that there are commodity prices. So these things can be, after they're recycled and sorted, can be sold in commodity markets for some prices. So the commodity prices drive the industry. So again, different things impact the pricing in these areas. The bottom line essentially is that accurate sorting. So like I said before, being able to very precisely say, okay, this is a stack of PET kind of plastic, whereas this is a stack of polycarbonate like plastic. That sort of accurate sorting is very important because that precision is what gives higher premium prices. And of course, the transportation costs can be very high. So efficient transportation, if you could make things flat and light and so on, also important factor. So I just want to emphasize, like I said in the very beginning, that you need to not only think about the technology, but also about what drives the market, what the technology is actually used for. So it's pretty critical to keep those things in mind. Now, we talked, it turns out the recycling of plastics is the most challenging because if you think about it, there are many, many different types of plastics: polycarbonate, polyethylene phthalate, polyethylene, PVC, polystyrene, all kinds of things. There's hundreds of them. And all of them, if you look at it with a simple camera, for example, like we were talking about using 2 cameras to do stereo vision, if you simply look at the 2 cameras, you won't be able to tell them apart. So if you take a picture of a PET bottle or a poly PVC piece of plastic, they will look the same. They're both transparent. So how do you tell them apart? And you need to be able to differentiate them in order to get the premium in the price. So this is where optics comes in, and the solution turns out to be something called near-infrared spectroscopy. And this is just a fancy term for saying the following. If you look at these 2 pieces of plastic, which look the same to your eye, but if you look at it with infrared light, they will look considerably different. Okay, and that's what's shown in this plot here. So this plot is essentially the transmittance as a function of wavelength for a variety of different plastic materials. So you can see, if you look, let's take the example of, let's see, the black curve is polyethylene. Okay, this curve here. Okay, you can see that is considerably different than, say, polycarbonate, which is shown here. Okay, so in other words, the dip has moved from 1.65 microns to, let's say, 1.72 microns or so. And this curve here essentially is a spectral signature of the material. And by knowing the signature, you're able to distinguish them. Okay, so the simple way you can think about distinguishing these sort of plastics is to simply shine a tunable infrared laser at a piece of plastic and have a photodetector behind it, so it measures the transmitted light, and you simply change the wavelength. and build up the signature. Okay, and if the signature matches some known signature of the material, then you know, okay, that's a match. That's polycarbonate, that's polyethylene, whatever. Okay, so clearly you can imagine the challenge here is how to do this cost effectively and very, very, very fast. So there's a lot of innovation that happens and still happening in this field. By the way, near-infrared spectroscopy is not only applicable to recycling plastics, obviously, it is used for many, many different things. Some of you might have seen a near-infrared spectrometer, for example, when you go to the doctor's office and they look for oxygenation in the blood. My daughter has asthma, for example, so when we take her to the hospital to see a doctor, they almost always put a little, it's called it's an oxygen meter. It goes over the thumb or a finger, and essentially it passes an infrared beam and a red beam actually through your finger, and it looks at the signature. And the signature of hemoglobin is different. And from that, you can figure out the quantity of oxygen as it increases and decreases as the spectral signature changes. So you can actually figure out algorithmically what the oxygenation of the blood is. And of course, there are many, many applications for this kinds of technology. So of course, again, like I said before, the key challenge is how do you do this very fast and at low cost? So the simplest approach is something called correlation spectroscopy, and it's almost common sense. So the way it works is that it's relatively inexpensive and simple. So you basically have a halogen lamp for the source, it's for the laser. So a halogen lamp means you have all the wavelengths. So you're not essentially picking one wavelength, you're essentially illuminating with all the wavelengths of light. So if you look at this spectrum, all these wavelengths go into the sample at once, which means on the detector end, you need to be able to distinguish the different wavelengths. So that's the challenge. So the way you do this in a correlation spectrometer, of course, you need a detector. So in this case, it's an indium gallium arsenide detector because you cannot use a conventional silicon detector because it's near infrared. We'll talk about this later, but it's below the band gap of silicon, so it cannot be absorbed. So you need something called indium gallium arsenide, which is a little more expensive, clearly. But how do you distinguish the different wavelengths? And that's where this thing comes into play. It's a filter wheel. Now, it's a very simple device, essentially a wheel that turns, and it has different pieces in its window. You can see little windows here. And those windows are filled with different kinds of plastic, essentially. And this wheel spins, okay, as the light passes through it. And you have a detector behind this wheel, which looks at the signal. At the same time, you also have another beam path where the light is passing through the plastic that you're trying to measure, as shown here. And you look at the correlation of the signal between these two. So if this plastic coincides with one of these plastics, then you will see a very similar sort of signal. And of course, you have to be very careful in terms of normalizing the signals and so on. So there's a lot of work that goes into calibrating these machines. But once it's calibrated, it's a very, very simple device. Okay, so essentially you try to correlate the plastic that you're trying to see with one of these plastics on your filter wheel. And you can also notice that it also has color. So it has a red filter, a blue filter, and I think it's a green filter as well. So it can also take a color image. So you can also distinguish the color. So for example, if it's a green Mountain Dew bottle versus, transparent Coke bottle or whatever. So you can also tell those things apart. So all of this can be done in a single machine. Again, you can clearly imagine the optical design itself is very critical because you need this to be extremely fast and as cheap as possible. Okay, and you'll appreciate this in the next few slides as well. So one of the things, one of the very interesting innovations that happened in this field is described here. It's the use of a diffractive optical element for low-cost spectrometry. Now, so if you look at what happens here is that you need to have this big halogen lamp, and you need to have this indium gallium arsenide detector, and you need to have something mechanical that's spinning, right? So this filter wheel is rotating mechanically. So of course you can imagine that's slow. So that affects the speed. So there are two things they were trying to solve. Could we make it could they make it faster? And could they also make it more compact? Again, they solved these two problems with this innovation. They essentially designed a diffractive optical element which takes a point source of light of many different colors, the whole the halogen spectrum, for example, and it essentially reflects the light and makes a point image at different locations for different wavelengths. Okay, and that so that is represented, by the way, by this vertical line here. So you can see that's blue, green, and red. But imagine that's infrared, right? Not visible. It's just shown as a schematic. So the diffractive element essentially forms a line focus of this point source, where this line represents the different wavelengths of light of the spectrometer. And of course, then you have a single point detector. So to make it cheap, so you're trying to reduce the cost of the detector instead of having a big CCD or CMOS array. You basically have a single point, so it's much cheaper. It's like a photocell, basically. And then their innovation was to essentially vibrate the diffractive element. So you can see it's moving up and down by 2 degrees about this axis. So in other words, it's rotating like that. Okay. Now, as it rotates, you can see this line essentially moves back and forth, that pattern movement. Okay. Now, the detector, of course, is fixed. As the pattern moves back and forth, different wavelengths come into the detector. Okay. So now you can place a plastic in between the detector and this image. And as you rotate, you look at the signal seen by the detector. And at each instant of time, you get a spectral signature corresponding to a certain wavelength. Now, this can be extremely fast because this is basically vibrating. It can go at the resonant frequency of a spring, much faster than a mechanical stepper rotation of a motor. Okay, that's the idea. So again, this is an interesting innovation. As an example, a photograph of one of these diffractive optical elements. They're fairly complicated, but the idea is that you make a master device and then you stamp them out like a DVD. So they can be very cheap. In fact, this particular device was fabricated by one of the early companies in Europe that used to make DVDs. Right now, the manufacturing is moved to Asia, but that's the idea. So it's an example of an innovation. Single DOE can be used for beam splitting, spectrum separation, and focusing. So it's pretty interesting. Okay, now so far we kind of talked about relatively small scale sorting, but the vast majority of recycling happens at very, very large scale material sorting. And this happens at the municipal level, city level, county level, and so on. Salt Lake, for us, we have the Salt Lake municipality, which actually does this, and you can go take a look at it. It's quite interesting. So very large scale waste. In this case, this could also be not just recycling waste, but also regular waste as well. So you might have a situation where there is not very common recycling, or recycling is there's not high participation of recycling. So even in the conventional waste stream, there will be valuable materials. So it'll be a complete waste to just send it to the dump. The municipalities decide that, okay, we will set up this sorting facility, which basically will go through the trash and separate out the valuables from the trash. And then you sell the valuables to make money. And this could be very profitable. Okay. So, but of course, it requires very large scale, high throughput sorting. And it's complicated. And typically, the volumes go in the order of tens of tons of waste per hour. So it's very, very, very high speed. You can imagine huge conveyors going meters per second. And this is all done optically with near infrared and visible spectroscopy. In this case, these machines tend to be extremely expensive. You can imagine not very simple like we just talked about, but imagine huge facilities, multi-million-dollar equipment, essentially. You capture spectra with high spatial resolution, which basically means that you can also do shape recognition. So you can tell if it's a can, if it's a bottle, or if it's a piece of copper or whatever. You can do all kinds of useful materials recognition. a few centimeters of high speed. Spatial resolution of a few centimeters. And the reason to do this is cost. Basically, aluminum, for example, you can sell aluminum in the order of 70 cents per pound, which is in 2016. It can be melted and recast in containers, other items. Plastics are a little bit less expensive, but still pretty. It's a very profitable industry in the order of $30, $60 per kilogram. This is a few years ago. Plastics that are turned into fibers, fleece, fabrics, etc. So it's very, very useful raw material. Also, of course, saves on the carbon footprint because you're using this material particularly for plastics, because oil is a direct raw component for plastic. This is an example of a large-scale material recovery facility, or an MRF. So they're very, very big, and in this particular case, it's instructive to look at this schematic here. So you basically have a huge conveyor belt which takes the materials. The materials comes in on this side, goes over here, and the useful stuff goes here. The less useful stuff goes here. You can sort them. And this is basically, you use kind of a pneumatic pump or something like that to push it. So this falls over here. But anyway, the intelligence is in how do you decide what to push. And that's happening here. Basically, you have incident light, which comes in at an angle, which is infrared and visible light. And the reflective light is collected by the scanner. So you basically have lasers, which are basically scanning in the perpendicular direction to the conveyor. So the conveyor is going this way, and it is scanning this way. And you basically have two, because you get the shape information from two with image processing. The scanner does spectroscopy and can do spectroscopy in a variety of different ways. And this goes at very, very high speeds. So it's another interesting example. Okay, so we have kind of talked about today about a non-traditional application of optical engineering in optical recycling. I've given you an idea of what the problem is, how people approach the problem, and how key innovations have happened and are still happening to solve various problems along the way, driven primarily by the industry. Okay, so I want you to keep that in mind as you start working on your projects this semester. Now, in the final part of the class, I want to show you the video made by one of the teams that worked on this particular idea of applying some innovation to recycling a couple of years ago. I particularly like this because this is simple, and the idea is interesting. So it could be commercialized. In this particular case, the students did not commercialize it, but you can imagine. So I just want to show you this as an example. So let me first change the audio.
Distributed Plastics LLC would like to introduce you to a distributed optical plastic sorting method by simply reading the SPI resin code on consumer plastic waste. Distributed Plastics LLC is backed by Bing Shen, a PhD candidate, and Joseph Bogue, a master's degree student, both at the University of Utah's Electrical and Computer Engineering departments. Currently, consumer recycling is done in a big box manner, whereby large trucks go from house to house picking up recyclables. They then take these recyclables back to the plant where they have to sort them, compact them, and bale them for sale. Although this big box sorting method is proven day after day, these sorters are expensive because of advanced methods of discrimination. These sorters use visual and infrared wavelengths, spectroscopy methods where actual elemental makeup is determined, X-ray imaging for difficult materials, and lastly, the human element for anything that might have been missed. Although these big box sorters are marvelous feats of engineering, they come at a large monetary cost, both initially and through time. Now, in a recent case study done at Salt Lake Municipal's Recycling Center, they recently made a $7 million sorting capability upgrade. This upgrade is a great improvement for them. However, if recycling in general is done in a distributed manner instead, these types of costs can be greatly reduced. Now, before we get into the innovative technology, we need to review plastic resin. Remember that plastic is a synthetic material made from a wide range of organic polymers like polyethylene, PVC, and nylon. These polymers can be molded into virtually any shape and are easy to recycle if kept in the same resin family. This is why it is important. Keeping these polymers together allows for efficient recycling and more dollar per bale. Notice the code, the SPI resin code on this plastic bottle. Now, simply put, our innovative idea is a smart garbage can. This smart garbage can will take your plastic bottle, find and read the SPI code, and drop it into the appropriate internal compartment. It is centered around consumer plastic bottle waste and will automatically sort it as you walk away. It has 8 columnar sections, 1 for each SPI code and 1 as overflow, with a center hollow section that will contain smart electronics. Above this center columnar section is a dome to top with an enclosure that holds the plastic bottle on an incline. When the bottle is dropped in, the algorithm reads the SPI code from the image, determines which bin to rotate towards, and opens a door and lets gravity take over to do the sort. Notice here in the prototype overview, a high-resolution camera sends an image to MATLAB. The patentable detection algorithm then decodes the SPI code and sends that value out via serial data to a microcontroller. The microcontroller then drives a stepper motor and actuates a door to open, dropping the bottle and sorting. Actual prototype results show a noise-induced hand-drawn images sent to MATLAB. MATLAB detection algorithm successfully detecting the SPI code and sending that data via serial to a microcontroller. Microcontroller then correctly drives a stepper motor to the correct SPI code location, and a LED will blink showing or simulating that a door has opened. Now, our claim with this market potential is that Salt Lake County conservatively has a potential for a 30% increase in volume and a 3x decrease in cost if using a distributed plastic sorting method. The nitty-gritty of this claim follows. Salt Lake Municipal per week has a conservative capacity of 336,000 kilograms per week. Another conservative estimate of our distributed methods shows 431,000 kilograms per week. That is a certain volume. Another conservative estimate over 30 years shows our distributed method costing $22 million, whereby the large big box sorters have a infrastructure, maintenance, and overhead cost of $70.5 million. Again, this reflects our claim as a 3x reduction in cost. Remember, Distributed Plastics, LLC, we thank you for your consideration.
Okay, so you get the picture. Let me just point out a few important points that they did. That's nice. First, they presented the problem. So they presented like what is the issue that they're trying to solve. Is the idea of making something distributed in terms of sorting as opposed to something centralized. And why? Because they believe the volume can be higher, the overall cost can be lower. Okay. 2, they presented an innovation idea. Okay, this is the way they're going to do it. They have the camera, they do a picture, they did some analysis, and this is how the machine would be. You know, they did some schematics and so on. Number 3, they did a build out. In fact, in the actual presentation, they brought little bucket with a little setup with Arduino controllers and so on, and they demonstrated it. They didn't demonstrate with an actual can, but they showed that, okay, if you take a picture of some of this code, they had a little emulation. They didn't have an actual motor. They just had a small motor which showed basically a pointer going to different locations, just to show that the whole thing works. So it's a good example of a build out. So something more than just a PowerPoint. And then, of course, they spend a lot of effort in doing some customer feedback, which actually we'll talk about quite a bit. It's the part of what's called the business canvas. They talk to people at the municipality, how people use it, and they did quite a bit of effort on that Excel sheet where they try to understand what's the value that it'll bring to the customer. Okay, so these sorts of things, and of course it feeds back into how the things, your innovation will cost, how you engineer the innovation, things like that. So this kind of feedback is really the real purpose of this class that I want you to get out of it. So make sure you appreciate this as you start with your first assignment. Of course, you don't need to think about the whole thing because it'll come along down the line, but keep the big picture in mind of what you're trying to achieve. So when you do your first assignment, make sure you think very clearly about, what are the problems today? Who are solving these problems? How are they solving the problems? Are there any problems that are unsolved? Could we solve them? Right? Really, that's what you want to think about, and you need to brainstorm. So this is not simple. Okay, so we're going to end here, and we can have some discussion about your first assignment. So let me pause this.